Hi everyone to this video about flow equations, and in this video I would talk a little bit more about specific flow equations from Darcy to Ergun, and therefore we first repeat the fundamental idea of flow equation, or maybe for some of you we just introduce it, but there is another video where we talk really in detail about this fundamental idea of flow equations. And today you should learn different models we have as flow equations, how they are built up, what do they describe, and how do they work. Sorry, there's a typo. But yeah, at the end you also should be able to understand the differences between these models, okay? Therefore, we first make a small repetition. So basically, flow equations are mathematical equations, and they describe the relationship of the energy I need for a flow, because here's a liquid going through a layer of particles, a fixed bed, and therefore I need energy to move the liquid. Liquid can go from up to down or from down to up. If it goes down up, I need additional energy to the gravitational field. In the other way around, I already have the gravitational field, so water will flow, but maybe it doesn't have enough energy to go through this packed bed, right? So this energy somehow is related to the result, and the result is the outcome. So how much liquid and how fast is the liquid? If you think this is a coffee filter and the coffee goes through, it's basically how much coffee you get and how fast you get the coffee. And at the end, there is of course also an influence of the bed itself and the liquid. So the properties of the liquid, the properties of the bed, particle size, porosity, viscosity of the liquid, and all these three things depend on each other, and how they depend on each other mathematically is described by flow equation. Okay, and the easiest one is can be related to Darcy. And Henry Darcy was a French engineer, and he was long time ago, around 1850, he was responsible for the water supply in Dijon. And to equip Dijon with clean water, he was the first, or to solve his problem, his task, he was the first who did systematic investigation about this question, basically about the water flow through sand. And therefore here you see the experiment. So we have a water input, we have a column of sand, a fixed bed where the liquid goes through, and all of this was equipped with pressure measurement systems, in this case two, but you also could have more. And with this setup, Darcy systematically did experiments. So he changed the water column, so a lot of water, a little bit of water, and this gives different pressure to the system. So he gets an idea about the pressure. Then the length of the bed, so basically that's the length of the bed, right? You can have a very high layer, you can have a very small layer, and this of course influences the flow through the layer. Then the cross-sectional area, so a thin bed, a thick bed, maybe one in between, right? The diameter here, that's the cross-sectional area when you look from the top. And the grain size of the sand. So you can change this sand in here with very fine sand, very coarse sand, or a mixture of these types. And by doing this systematically, he was able to figure out this equation. And this equation is an empirical equation and relates the fluid velocity to the pressure drop along the bed. And this depends on the velocity, on the pressure drop, but also, of course, on the viscosity of the liquid, right? You can imagine that water flows much faster than honey through the system. So the velocity is important. The length of the bed, so how long is the layer, or how high is the layer the water has to go through. And then he has something called the permeability. The permeability is not so easy to imagine. It's a very, let's say, black box idea, so you go very far away from the bed without describing it in detail, but basically how good the water goes through this layer is described by the permeability, right? A high permeability means the water goes very good. A low permeability means the water cannot go so easy through this layer. And of course, we also can express the velocity a little bit different, and this is the change of volume over change of time, so volumetric flow rate divided by the cross-sectional area. So there is the cross-sectional area of the bed in this equation. And I rearranged this equation here because most flow equations are written in this way, and I want to have all of them present to you in the same way. So pressure drop divided by length, and pressure drop divided by length in this case is velocity divided by permeability multiplied by viscosity, right? A very, very simple equation. The trick is a little bit this K value. You really need to know it, right? Viscosity is easy. Velocity you can measure, you can calculate. Pressure drop you can measure, you can calculate. But getting the K value is not that easy. Okay. But in this way, he made Dijon to the second cleanest city behind Rome at this time regarding drinking water quality. So very successful. And the basis was his systematical investigation and these simple equation. So later we have a little bit more advanced equation. This is the so-called Hagen-Poiseuille equation. And this equation is interesting for different point of views because it describes the pressure drop as a flow through a long cylindrical pipe. And this counts for laminar flow, creeping flow, so very low velocity, no turbulence, laminar flow. And his approach is to say, okay, we have a bed, could be sand, could be a coffee filter, whatever, and now we make an easy assumption. And this assumption, I don't do experiments, I do math. And in my head, the liquid goes to a very complicated system. But it's not easy to describe this complicated system. So I imagine that there are small cylindrical pipes, and they go just straight through. And the water goes just through these pipes. So there are no particles, and the diameter of the pipe tells me how fast the water goes through and how much energy loss I have due to friction and so on. So it's a very theoretical approach, and basically it can be derived from the Navier-Stokes equation, and he also derived this equation from the Navier-Stokes equation by balancing the pressure gradient with the viscous force, right? If you balance these two parts of the Navier-Stokes equation, you will end up with a Hagen-Poiseuille equation. And this equation says that the pressure drop divided by the length of the bed depends on the viscosity of the liquid, the volumetric flow rate, and the volumetric flow rate can be represented as the velocity times, which, right, so we have here dv dt, this is volumetric flow rate, and now you put this here, velocity times a would be dv dt, or v dot, it's the same, and a porosity. So in the porosity is hidden somehow that we have a particle system, right? And not only pipes, but basically the radius of the pipes is mimicking the gap between the particles. So it's a quite theoretical model. The application is somehow, yeah, it's not the best, let's say it in this way, but it's theoretically a very important equation which you should know. And then there was another guy, or two other guys, Carman-Kozeny. And they said, okay, all what Hagen-Poiseuille were doing is very nice, but it doesn't really work because it's too theoretical and we don't have these pipes. But what we can think about is if we have all these particles, there are small gaps between these particles. And instead of huge cylinders going through the bed, we can consider always small particles, and the pipes are between these particles, right? So we have a lot of small pipes hidden in the system. And in this way, also for laminar flow, they found that the pressure drop divided by the length is 150. This is empirical, 1 minus porosity, viscosity, velocity, and particle diameter squared, and again porosity. And the big change is that here we have cylinders which go, or cylindrical pipes which go just straight through the bed, and the liquid goes through, which realistically doesn't make sense. And here they take this idea and put the idea to the gap between the particles. And with this, they are now able to implement the size of the particle, which is a basic property we can measure, right? We can take the sand particle from Darcy's experiment and measure their size, and this would be dp. And the porosity of the bed. So we can measure the porosity, how the particles are reorganized. And basically this is a much, much better description than the permeability of Darcy, because in the permeability this is hidden. or this is basically hidden, right? And this equation holds for flow through packed beds with particle Reynolds number lower than 1, right? Because this is laminar or creeping flow. And if the Reynolds number is much higher, we would have the equation would not give a good result anymore because the energy loss is too high. And this is now considered by the last equation you maybe know from the video before, because when we make this theoretical derivation, we end up at the Ergun equation, and this is basically the extension of the Carman-Kozeny equation, the equation you saw before, to all kind of flows, laminar and turbulent flow, so higher velocities, but again a fixed bed, packed bed reactor. And here you see the Carman-Kozeny equation, and this is the laminar part, and the laminar part means there's only friction, so the liquid only has friction. If you want to learn more about this, think about drag force. There's a video about drag force explaining these term and these term. And the other term we have now, this is the additional term, is the pressure term, because when it comes to pressure drop, which is basically friction of the liquid with the particle and a full bed of particles, not a single particle, we have friction plus pressure. And Ergun now describes this in a full equation where we say, okay, this is friction and this is the pressure loss due to the turbulence in the flow. And this goes with velocity laminar, and this goes with velocity square, and we see in between the properties of the bed in terms of particle size and porosity. And here we have the fluid viscosity and the density of the fluid, right? The density of the fluid is important for the pressure difference, and this is important for the friction. And with this we have a very good equation which we can use to in detail describe the flow through a bed, but it's also much more complicated than the Carman-Kozeny equation because we have these pressure terms. Okay, so this picture is important for me to sum up a little bit, because I presented you the equation, but I said I want that you understand also how these models, what are the assumptions behind the models, right? And Darcy is basically a very simple model where you said, okay, there goes a liquid through a bed. I don't really know this. I don't know what it's in here, but it has a permeability, and the permeability is a value which tells me how good this works. Okay, so I cannot make a statement about the particle system here. And then we have Hagen-Poiseuille, and Hagen-Poiseuille said, I don't care much about this particle system here, but I say the liquid goes through cylindrical pipes, and these diameter of the cylindrical pipes are somehow related to the property of the particle and of the packed bed, right? And then we have Carman-Kozeny and Ergun, and they said, no, we need to know a little bit more about our packed bed, about our particles, about the system. And they really consider the packed bed as a packed bed with a given porosity, with a size of particles, also size distribution, whatever, right? And the only difference between Carman-Kozeny and Ergun is that Carman-Kozeny is just laminar flow, low velocities, and Ergun is also considering higher velocities, so also turbulences. And a general idea of them was also that you have all these pipes here between the particles, right? Here's a small pipe, here's a small pipe, here's a small pipe, here's a small pipe, here's a small pipe. And this is how they end up with their equation. So now if you want to task a little, or if you want to train a little bit, I have some tasks for you. And the first task is repeat the flow equation and explain the difference in the models and the equations between them, right? So write down the equation, think about the assumptions behind them, how are they different, what is equal, and how are the variables related to the model, to the idea of the equation. Then I would really recommend to plot all these models as a function of velocity for different particle sizes and as a function of particle size using Python. So means you take the model and you take certain particle sizes fixed, and then as you plot the pressure drop as a function of velocity, or you set the velocity fix and plot them as a function of particle size and look at the differences. Look how the models evolve, okay, and how they differ and where they're equal. And this gives you a very good understanding of this, of mathematical understanding of the models. And then finally, there is a last task, and this is you're a young process engineer at a fertilizer company, and the company operates a Haber-Bosch reactor where nitrogen and hydrogen gas react over a packed bed of iron catalyst pellets. So it's basically the picture I showed you for the flow equations, but the management is considering replacing the current catalyst pellets with smaller ones to boost surface area and increase ammonia production, right? So the idea is to use smaller catalyst particles to have more surface area, to have more output. And your job is to check whether this change would cause a too high pressure drop, or if which would give a much higher compressor cost at the end, right? So you check if you decrease the size, is the pressure drop exploding? And therefore you have here the numbers you need, the diameter of the pellets, the porosity of the bed, the density of the solid, really high, right? Viscosity of the liquid, and the superficial velocity of the fluid. And what you should do is first calculate the pressure drop per meter of a bed with the current pellets, and then break down the contribution of the friction term and pressure term. So it gives you a hint which equation you should use, and which of these dominates. Do you have more friction, or so is most of the pressure drop coming from the friction, or most of the pressure drop is coming from the pressure difference term? Which one dominates, and could Carman-Kozeny equation be used instead? So can we use the Carman-Kozeny equation instead, the one you use here? And if you now replace the pellets with smaller one, half of the size, so 1.5 millimeter, recalculate the pressure gradient and think about the trade-off, more catalytic surface area versus higher pumping energy. And with this, I would to sum up the video. I hope I repeated shortly the fundamental idea of flow equations and give you a detailed insight into the different models, and you'll get to know them. And I hope also you can understand the differences between them, right? What are the assumptions? How do they work? How are the equations different? And so on. And with this, I would like to end the video and really thank you for watching. And if you have any questions, just let me know.